Hi Year 12s. So this first video will be about topic 1.1, global warming and climate change. Now the typed text are the excerpts from the SACE chemistry outline. Under those I've chucked in some of my own notes which will supplement what you'll find in the workbooks. Now first things first, on the left here you'll see a diagram showing the Earth and the Sun and radiation traveling between the two. The first step you'll see is solar radiation in. So that's these lines coming from the sun towards the surface. Some of this light, particularly on parts of the Earth with high albedo or high reflectivity, will send that light straight back into space as the same color as it comes in, or at least invisible light. But a lot of this light will instead be absorbed by the Earth's surface. Now, once the Earth has absorbed that light, it will heat up, and then that will radiate the light back out into in the direction of space in the form of infrared radiation. Now, this radiation is traveling out from the surface of the Earth, but as it's traveling through the atmosphere, it will encounter specific molecules, known as greenhouse gases, that are capable of absorbing that infrared radiation and heating it up, as well as re-radiating it back towards the surface and into the atmosphere. So when we have this occurring, this trapped heat will increase the temperature of the atmosphere. Now, this diagram that I showed you on the left with the Earth, that is a careful balance of energy in and energy out. And if anything is disrupted, it can disrupt this balance. For example, if we were to increase the concentration of our greenhouse gases in the atmosphere, we will trap more energy in, which will lead to increased temperatures. Now, often these will happen more quickly than natural processes, which is the issue that we're seeing. Now, for this next one, we're talking about anthropogenic increases in greenhouse gases and how it disrupts the thermal balance of the atmosphere. Anthropogenic increases specifically refers to greenhouse gases that humanity has contributed to the atmosphere, which is much more, which is a lot quicker, I should say, than the natural sources. Now, this diagram here represents the measured atmospheric CO2 concentration over time, along with an overlaid global average temperature. Now, obviously, this is a sketch, but the actual graphs show something very similar. Whereas our atmospheric concentration, CO2 concentration rather, goes up, we end up. So as this trends up, we see a similar and corresponding trend to the global average temperature. Now, because of this increase in temperature, we have seen an acceleration of climate change and the negative consequences associated with those changes for life on Earth. So as this climate change occurs, living organisms are unable to adapt and evolve quickly enough to be able to survive, causing a loss in diversity and generally collapses of ecosystems. Now, this next section is talking about another consequence of the increase in carbon dioxide concentration in our atmosphere. More specifically, we're talking about the acidification of our oceans. Now, I've got some chemical equations here, and I'll just be adding in some extra details into these equations. So one thing that's missing from these are the chemical states. So we start with gaseous CO2, and when that comes into contact with water, you can make aqueous CO2 or dissolved CO2 as a product. So this first one this number 1 represents the dissolution or the dissolving of gaseous carbon dioxide in water. Now, once it's dissolved in water and we have aqueous CO2, it can actually react with the water to form, so the liquid water to form aqueous, so dissolved carbonic acid. Now, as the name suggests, carbonic acid can act as an acid, which in this case means ionizing, so turning into H+, again aqueous, and hydrogen carbonate. Now, this particular, this step 3 is the one that we're looking, well, it's most important in this particular case, in that it releases a H+. So releasing a H+, which is our basic unit, our most fundamental unit of an acid, causes the ocean itself to become more acidic. Now, these next set of mathematical equations are describing how we can work out, or at least the relationship between the pH of a solution and the concentration, so the pH over here, and our concentration of our hydrogen ions. If you happen to have the concentration of H+ ions in your solution, you can work out the pH by taking the negative log base 10 of that concentration. Now, you are generally going to be using a calculator for this purpose, and on the calculator, the button is the log button. LOG is log base 10. You can mess around with other things, so you can do logs of some other base, but those will be different buttons. There's even an LN button, which is similar, but it's instead of log base 10, it's log base E. Regardless, if you need to find the pH and you have the H+ concentration, you can do it using this equation here. Now, if instead you are given the pH and you need to find the H+ concentration, we can mathematically invert this first equation into this second equation here. So, given the pH, you can, using a calculator, 10 to the power of negative pH will give you the H+ concentration. Now, as you can see just here, I've got a few other equations written in here. Those are pretty much the same as the ones we've done so far, but instead of pH, it's going to be POH. So H pluses are our fundamental unit of our acid. Our fundamental unit of a base is hydroxide, so OH minus. And you can find the POH as well. Similarly, if you want to find the POH, you take the negative log base 10 of our hydroxide ion concentration. And as per the one for hydrogen ion, if you take 10 to the power of negative pH, that will give you your hydroxide ion concentration. Now, the reason why we look at both of these is because they are related to each other via this equation just here. If you take the concentration of our hydroxide ion and you multiply it by our proton, our H+, you are going to, in water, you're going to get a value of 10 to the power of negative 14. Now, if you, for example, you increase the amount of hydroxide ion concentration, you must decrease the value of H+, so that that value is still constant. Conversely, if you decrease this one, you must increase the other again to keep that value, so the product of these two values, constant. That 10 to the power of 14, by the way, is referred to as Kw, which is our ionization constant of water. So in water, if you increase the H+, you will decrease the OH minus correspondingly. Now, mathematically, they are related in this way as well, which obviously it's very closely related. If you have the pH and you want to find, if you have the POH and you want to find the pH, you can use this formula here. again, if the pH were to decrease, something becomes more acidic, then that will make the pOH increase, so that the sum of both these values are always equal to always equal to 14. Okay. Now, moving on to the last section of subtopic 1.1, we have a few more equations, but this time we are looking at the direct effect of our acidification of the ocean, so our pH decreasing to low pH, on the calcium carbonate in the water, which is important as many marine organisms utilize this substance to create their shells or their structures inside their bodies. Now, this term here, equilibrium, will be investigated much more thoroughly later, so I'll just do an introduction of it here. Important for you to know is that equations are not just simply reactants becoming products. They are actually an equilibrium where you will have some reactants, some products as you've written them. So reactants on the left as I've written them, products on the right, but you're not always going to have all of your reactants become products. You're often going to have some balance between the two. So in this particular case, if we have our CO3 2-, so that's our carbonate ion, and you have H+ in the water, they can react to form HCO3-. Again, not all of them will react. You'll still have all three of these substances in the solution. Now this first one, I am going to number them just so it makes it a bit easier to talk about. We have 1, we have 2, and we have 3. Our first one, the importance of this one is that it's a reaction that happens between our carbonate ions that are free carbonate ions floating around in water, reacting with H+. So remember that at low pH, we have increased the amount of our H+ in the water. As such, you're going to have it more likely to react with our CO3-, so we're increasing the amount of our H+, it's going to react with our CO3 2-, and it's going to form some hydrogen carbonate. So you're removing our CO3 2- from the solution and forming some hydrogen carbonate. Our second equation is focused on our calcium ion. Now, if you have CO3 2- in the water, a organism or a calcifying organism will combine it with the calcium ions to form solid calcium carbonate. Now this substance here is important because that's the stuff that these organisms use to make their shells, and you require both CO3 2- carbonate and calcium ions in the water. As you can see from the first equation though, if you have a more acidic environment, you're going to decrease the amount of CO3 or carbonate ions in the water, making the second equation less likely to, or less available, or less likely to happen. Now our third equation is talking about further effects of increased acidity. Now if you have an increase in acidity, you are increasing the amount of H+, and what this does is it reacts with our calcium carbonate, our existing calcium carbonate, in the form of the shells and structures of these organisms, and it turns them into free calcium ions, water, and gaseous CO2. So essentially it is dissolving the existing shells, which is going to stop these organisms from being able to protect themselves and generally remain alive. Now this bit down the bottom here, it's just a little bit more information about chemical equilibriums. What's important for you to know for the moment is that reactions can be pushed forwards or backwards, so you can make more products or more reactants form by messing with the amounts of either the products or the reactants. If you add reactants. So you add something to the left-hand side of any of these equations, you're going to make the forward reaction occur to a greater extent. So in that case, actually I'll finish off this one and then I'll talk about it a bit more. Conversely, if you add products, so for example up here, if you have for equation 2, let's go to equation 1. If you put some more hydrogen carbonate into the water, you're going to make the backward reaction, making the reactants happen to a greater extent. So if you increase the amount of this, you're going to make the reaction go further forwards. If you decrease the amount of this, you're going to make the reaction go backwards. Similarly, if you increase the amount of products, you're going to make the reaction go backwards. Again, you will learn a lot more about this in further sections. So that's all you need to know for the moment.